everyone enjoyed the gnocchi. All right, so we're going to talk about distributed tracing at Facebook and Uber. So kind of a fun story. As Yuri and I had submitted separate presentations for this, and as we went through the process, we kind of realized that we were both using tracing to scale at Uber and Facebook, but sort of in slightly different ways. So Uber's really using it to scale by scaling their engineering work, right? By making it easy to find a problem in their big microservices architecture. And Facebook's really using it to scale our systems, right? We're using it to identify bottlenecks, perf and efficiency bottlenecks, and knock them out. So we're going to go through that. What is tracing? What does it have to do with scale? We're going to go through a case study of how we do it at Facebook, how it's done at Uber. Sort of close out with some stuff you can take away if you think it's something that would help you, and leave a bit of time for questions. So with that, a little bit more about me. I am Michael Bevel-Aquilin. I'm a software engineer on Canopy, our tracing system, and I've written a book on functional programming stuff, if that's interesting.
Thank you. Hi, my name is Yuri. I work at Uber on the observability team for about 4 years. I started the Jaeger project there, which now became a cloud-native foundation project, open source distributed tracing. I also worked a lot on open tracing and open telemetry that we'll talk about briefly in this talk. And this year I published also a book on tracing, so it was kind of my experience from Uber and evolving this system. So what we want to talk about really is how tracing helps scale. Right, distributed tracing has been known for more than a decade already, but is gaining popularity recently, and there are a few trends, I think, in the industry that kind of are conducive to that, and I want to touch on this. Actually, the first one, I think in the first talk we already had a pretty good description of this scale-out problem, and as we now have companies serving millions of users, we can't run it on one machine, so we started building distributed systems. The other trend is kind of, you can think of it as scaling the software itself, right? So you can develop a monolith and make it bigger and bigger and bigger and deploy the copies of it on multiple machines, but at some point, it becomes an organizational bottleneck. You can't really have that many developers working on a single piece of software. It creates all kinds of issues from deployment to on-call duties. Like imagine if you own 100 of a code base in a system and then you're on call for the whole thing. Like how do you even do that, right? And so the solution to that people came up with are microservices, our microservices architectures. And I showed these microservices on the right side with the different shapes, because one of the interesting aspects of microservices is that they can be now, unlike monoliths, they can be in different technologies, different programming languages. And that creates even more unique challenges with managing these things. And the third trend that has been happening in a few years is really evolution of our asynchronous programming models, right? Back in the early 2000s, you would have a typical Java application server running n threads, and each thread would execute one request at a time, right? And then we came up with all kinds of different frameworks that are based on futures, promises, event loop-based frameworks, where a single request can be handed off between multiple threads until it's processed within a single application. And so that complicates a lot, like observability of that system. And finally, we arrived to sort of microservices world where the same thing is multiplied by the fact that like one single request can jump not only between threads, but between different computers even, right? And so understanding what that system is actually doing becomes really, really hard. So this is a diagram rendered by Jaeger, so like a topology service map of Uber, right? It's probably 2 years old now. The edges are communications between services. The size is roughly like the traffic. And so every time you hit a button on your Uber app, a transaction goes through that architecture. And that transaction can touch dozens of services and potentially hundreds of nodes, right? So it's almost inconceivable to be able to operate an architecture of this complexity without very good observability. And observability specifically into distributed transactions that touch so many services. You could get that to like the traditional monitoring tools wouldn't get you there because they only give you like a very narrow view. But in order to get that visibility into the system, you need very robust instrumentation to be in the application so that we collect all kinds of telemetry. And doing that is actually a pretty challenging problem, as we'll talk about this. Like, imagine if you have to write tracing libraries, for example, in 5 languages and 10 different frameworks for every language for different database drivers. So that's a lot of work. And on top of that, our modern software is very composable. So if you're writing a service, you may need some like server-side framework to handle HTTP requests. You may need some like RPC framework to handle outbound calls, right? A database driver, etc. And so usually these are not like components specific to your business. You don't want to write them. You just pick them from open source somewhere, right? But then if they don't understand what they're doing in terms of observability, you're not going to get a coherent system from that system, especially for tracing, which relies heavily on context propagation. And so we need all these components to speak kind of single language, even though those components are written by hundreds of different people from all over the world. And that's why I want to call out to a couple of projects which have been like brewing in the industry the last couple of years. One is OpenTelemetry, which is actually brand new, but it's a merger of 2 previous existing projects, OpenTracing and OpenCensus. And it's an API for collecting telemetry, right? It's a unified API where essentially you can pick it up for any open source software, and hopefully it will be there. And so we kind of want to live in a world where all software, all frameworks that we pick from open source come with telemetry built in, so that we don't have to re-instrument everything. And the second project is a working group in W3C, which is focusing on data formats, unified data formats for tracing specifically, so that if you make a call to Spanner, Spanner would understand your trace context, for example, right? So that, and it also works on an out-of-band trace data format. It's interesting that Uber has been sort of the early adopter of open tracing. Virtually all our instrumentation is open tracing internally, whereas Facebook, they started pretty long ago compared to all this fairly new project, and so they had to do that on their own. And so they kind of ran into various challenges that Michael will talk about.
So yeah, so that's right. Like, you know, one of the interesting things as we were pulling this together was like, we don't use the stuff that's being standardized for instrumentation, which has some benefits, but a lot of pain as well. So I'm going to talk about that a little bit. So yeah, we do something different. Partially it's for historical reasons. We just started early. But partially also we had sort of a set of requirements that are a little bit different than what most distributed tracing systems do. So we wanted to use our tracing system both for that sort of broad-based distributed trace Yuri mentioned, but also for these really detailed performance traces of individual systems, right? Individual sort of nodes or individual sets of systems in the overall Facebook architecture. And the reason for that is we were sort of building out all these different tracing systems and then like duplicated tooling around them, duplicated instrumentation, duplicated processing, duplicated viz, and that got to be, you know, very, very expensive. So we wanted to handle both of them. You know, so we sort of started off with, you know, the distributed tracing one was this thing called FBtrace, very, very much like what Yuri just described in terms of the data model, the instrumentation, but that sort of data model, you know, which you just kind of have nodes in your system, and then you've sort of got, you know, points that represent when the request is sent and received and so on. Very similar to the stuff that's being standardized, but with different names. It wasn't flexible enough to represent all of those different tracing systems, especially the more detailed ones. So what we ended up doing is coming up with a unified data model that could represent both the really detailed traces and the broad traces. It's called Canopy. There's actually a really good paper about it. And then standardizing on that. So now we did that transition. It happened before I joined the company. We've got a consolidated platform now that lets us handle both of them. We've got one set of tooling, one set of viz for everything, but nothing's free. And sort of in our case, one of the ways we're paying for this is we're still actually going back and ripping out that old instrumentation, right, from sort of the old tracing systems. It's years later, and you know, I have like a pile of tasks that's like this big of like, hey, could you go and like rip out that thing that's been deprecated for 2 years, dear engineer? No, I guess I'll do it. You know, so it's sort of like, you know, like it looks like that, right? But unified tools, unified, you know, viz, really great. So I'm actually going to talk about one of the bits of tooling we have that's a little bit unique a little more. So one of the unique bits of our tracing system is that we actually have a built-in stream processing system, or really sort of a generic processing system for traces that lets you work with an individual trace in a notebook, lets you sort of work with a batch of traces, and then it lets you process a stream of traces as well. I think that's kind of one of the themes that also came out as we were pulling this presentation together, is that looking at an individual trace is useful, but you actually need to be able to work with them in aggregate to get the full value of them. So we have a built-in trace processing system that you get sort of this Python DSL. You can spit out aggregate data sets from a population of traces, from a stream of traces, and we do a bunch of interesting things with that. And one of those interesting things is actually we have a tool that lets us sort of compare these populations of traces for performance regressions. So basically, you've got a set of traces from, you've got a set of traces A, a set of traces B. Maybe A comes from before an app release and B comes from after, and so on. And then you can get sort of this visual representation of what changed, what was faster, what was slower, what was more expensive, what was less expensive. And so we've been doing this for a while. And sort of as we were pulling this together again, we realized that Uber had sort of a very similar set of visualizations they were building out, but to do debugging of distributed systems problems rather than these sort of perf and regression things. So.
Yeah, it's interesting that the sort of use case of using tracing for the classic purpose of performance optimization and efficiency so far hasn't really picked up at Uber. We have power users who do that, but like general engineers typically don't do that. And instead, we primarily focused our tracing efforts on dealing with the microservices complexity, because Uber is one of the most complex architectures probably around there. And so here is at the top it's one trace, right? It's, I think, like a driver goes online. So we can see here it hits 30 services. That's a real one. And then it contains about 100 RPCs. This is one single distributed transaction, right? And at the bottom, we see this is like a Gantt chart. It's a mini view of the Gantt chart of that trace. And so the issue is that if you are an engineer, if you want to try to like what's wrong with this thing, and you're trying to debug it using that kind of visualization, the Gantt chart, it's almost impossible, because if you look at it in a regular zoom view, you would have to scroll like 10 pages even to find anything. And so that's why we decided that we kind of need different types of visualizations for analyzing the performance. Specifically, we realized that if your goal is to understand what was wrong in one request, then looking at this request may not be actually the most optimal thing, because let's say you're interested in why it's so long, right? Well, you can go and say, oh, this segment was the very long one on a critical path, but maybe it's always this long. Maybe that's not what's wrong with this request at all, right? So actually doing the comparison with something else is a lot more, usually a lot more revealing than just looking at one single thing. And so so for that reason, we sort of started with a tool which compares two traces. You can think of it as like you pick one failed trace and you pick another one which you think is the typical behavior of the system. I'll speak about the typical behavior, though. All right? And so here it is. You can see that, like, oh, you probably, I don't know if you can see it, but the left, there's two traces, left A and B, and the trace A has like 500 spans. So clearly, we don't see 500 data elements on this graph, right? So one of the things that is unique in this visualization is we condense the information, because this is impossible for a human to comprehend 500 data points on one screen. So we kind of collapse individual spans within the service. We also remove repeated call paths so that so we can just represent it with a single edge. And then after that, we're doing essentially a structural comparison of two graphs, right? And we took the inspiration from like a code diff tools, because everyone is familiar with that, and we use the color coding to display that. And so here we see that the gray area at the top part represents that things are the same in two traces, right? So there's not particularly interesting thing. But then section at the bottom shows that there's lots of red nodes, meaning the stuff is missing from the trace B. And so a lot of computation that typically happened in A didn't happen in B. So you can kind of immediately, your attention is drawn to that section of the graph, and that's the power of the visualization, right? And Section 3 shows slightly light colors, green and red, is because it's not exactly complete structural difference, but the number of calls is slightly different, so we kind of indicate that. And finally, as I mentioned, you look at this area and you try, okay, well, this is clearly something bad happened. In this specific case, again, this is a real production trace. It was from Uber Eats app, and I think the system tried to charge credit card, realized that there's a problem with credit card, and roll back the transaction, right? So it's kind of logical that, okay, yeah, the big chunk of the execution wouldn't happen in this case. So one of the things that this tool also allows is that it's deep linked into the regular trace view. So this is a Gantt chart, although you probably can't tell really because I expanded this one span. But when you expand the span within the Gantt chart, you can see a lot of rich details about it. So it's like a stack trace, the actual error saying you have a credit card balance or something. And so you need to go and, like, that points you to the root cause of this issue with this specific trace. And yeah, the richness of the details is kind of a subject to instrumentation, how good your instrumentation is. We also experimented with other types of sort of color coding. And the example I mentioned earlier, what if you're interested in why one trace was longer than another, right? In this case, I don't know if you can see it, but 2.7 seconds versus 4 seconds, right? So like the trace B much longer. And so we used a heat map approach to color code the nodes by their duration, by contribution to the overall latency of the trace, right? And so we can see that basically your eye kind of immediately draws the path of where the things were different from normal trace by the latency of the spans. And then if you kind of drill down into one of them, you can see, okay, well, this is like 1 second longer than usual, and it constitutes 30% of the overall latency here, right? And so that's a second type of visualization with two traces, right? And so what's different about this approach? One is, like, as I mentioned, it surfaces a lot less information about the trace so that you can actually comprehend the overall distributed transaction rather than dealing with thousands of spans. And it emphasizes the differences between things rather than letting you drill down into one thing. And finally, by sort of varying the types of color coding and types of comparisons, you can like narrow down to the specific use case. So like if you're interested in when the request went, then you may want a structural comparison. If you're interested in the latency, it's like a duration comparison. And there are potentially other things that we can do, right? However, there is one challenge with this approach, and that I alluded to at the beginning. I said, you have to pick trace A as the normal behavior of the system. How would you know that, right? How would you know out of a million traces that this is the one that represents typical behavior? That's a big challenge. It's like up to the user to actually pick the right baseline for comparison. And for that reason, we went and we decided to kind of do what Facebook does for performance comparisons. Let's compare it with an aggregate rather than a single trace, right? So the trace A, or rather on the left side, is the aggregate of kind of successful behavior of the system that we observe over time. We compute a statistical model of that, and then we do the exact same technique of comparing two graphs where one of them is not real trace, but an aggregate representation. And so the display itself is very similar. It uses slightly different color coding, but conceptually it's the same. Right, so I have these annotations, I think. At the top, you see, like, this is the service, this is the endpoint. There's also request and response at the top that you can kind of, the payloads, you can drill down if you want to understand what happened. And as always, we always have a link to the underlying trace. So if you want to drill down really to the fine details, you can go there. And you can actually go there from individual spans with a deep linking. That, like, people find it very useful. So the view is similar, but the color coding here is sort of like white means the same structure, black means it's missing in a trace that we're investigating versus the aggregate model. And the nodes are sorted horizontally, like top down, so that it kind of, you can read that trace as a narrative in a way of like these things, then this, and this. It's not always the case. Sometimes it's parallelism, but in many cases, executions are kind of can be laid out this way. And as before with the trace diff, section 4 kind of clearly draws your attention, saying this whole thing went wrong somewhere in the bottom of this section, right? And you can, that allows you to sort of pinpoint to where the issue is and try to investigate what specifically happened. And one more thing here is the red nodes indicate the errors that happened. We have certain threshold because some errors are retries that they're not really like breaking the trace or transaction. In this case, it was something serious, and you can mouse over to get more details. And even more specifically, you can click on it and get like very detailed panel on the right side, which says, yes, these are the tags and logs from the span, where it explains what actually happened, and it has concrete error messages over there. So the two main differences of this approach from the just like regular trace diff is that it gives us a much broader context of comparison and the confidence that we are not actually comparing something with a complete outlier. We're really looking at representative behavior of the system. And the other thing is that this tool has like a single purpose, right? We did not design it for specifically optimization for performance, right? It's for root cause analysis. When we deploy this tool, we actually had testimonials from our users, first responders, and the way they operate is that they get an alert of some business metric saying people can't take trips in Fresno, right? And so how do you go from there to, oh, there's this service X that's actually misbehaving in some way? That's very hard challenges when there's 30 to 50 microservices involved in every request. And so they typically would go through logs and metrics and trying to kind of navigate this path of a transaction and figure out where the problem is. Once this tool became available to them, they went from 30 minutes of investigation to 2 minutes. And so that was very successful. So as a summary, I think we sort of use microservices to help us scale our organization, but it brings with it other challenges, that especially the observability and operational challenges of that architecture. And tracing has been proven as a very useful tool for us to actually understand that complexity and manage it.
All right. So just to sort of summarize, the distributed tracing really can help you scale both your engineering organization, right? Especially if you have microservices. How do you find, the root cause of something quickly, right? 2 minutes instead of 30. And it can help you knock out perf and efficiency bottlenecks as well. So there's sort of like two big ways you can use tracing to scale. I think some other interesting stuff that sort of came up as we were going through this was, in order to get the benefits of them, first of all, you need really robust instrumentation. So I'll touch on that a little bit before we go. And then the other one is that you actually need to be able to work with sets of traces, right? You actually need to be able to produce aggregates off of populations of traces that sort of might represent something interesting. A baseline, right, of a performance system, or a baseline of a functioning system, or a system before and after a change, and so on. So those are two really key things: is robust instrumentation and the ability to work with traces in aggregate. So on the instrumentation one, again, please don't build your own. Take a look at OpenTelemetry. Take a look at the stuff that's going on in the W3C. It's really, really great stuff, and it's really a robust set of things. I'm really excited that this stuff is being standardized. It's been around for over a decade now, right? So having it be standardized and having an ecosystem, right, of people doing this in a way where everyone can share and collaborate is a really, really exciting thing. So that's what we got.